Hello everybody, welcome back to this training on natural language processing. In today's discussion, we'll actually do some hands-on and we'll see how we can implement topic modeling using Latent Dirichlet allocation and some of the R packages. So we've already discussed about what topic modeling is and what is its core purpose. So just a quick recap. So in topic model, what we try to do is, if we have a collection of text data, we try to do some unsupervised learning on text. So the idea is to segregate the text data into some disjoint groups, and the groups are to be formed in such a way so that each group is homogeneous with respect to the context or the topic which is present in the content of the text, and between groups there should be as much heterogeneity as possible. So very much like unsupervised learning that we do with numeric data, topic modeling is exactly the same analogy of that using text data. And one of the algorithms to implement topic modeling is Latent Dirichlet allocation, and we will now see how we can implement that algorithm using R. So in terms of the core LDA task that we have and that we have seen when we were discussing the theory is we want to factorize the document term matrix into a product of two matrices, right, using some matrix factorization approach. And these two matrices, they will have some very special interpretation. So one of the matrices will be the matrix of topics and terms, and the other matrix will be a matrix of topics and documents, and respectively these matrices will give us some of the conditional probability distribution. So the matrix of topics and terms, it will actually give me the conditional probability of terms given every topic, and the matrix of topics and documents, it will actually give me the probability distribution of topics given every document. Right, so the code task is to do this matrix factorization, and if you are able to do this matrix factorization, then we can extract out these two individual matrices and then draw additional insights from them, right? So that's the code task. Now, in order to achieve that, what we will need, along with quantdata and read text, which are the libraries that we have been using right since the beginning of this course, we will need few other libraries out here. So read text is obviously we are using it for reading the text data, and quantdata is our core NLP package that we are using here. Along with these two, we will also use something which is called topic model, which is what is required to implement the Latent Dirichlet allocation algorithm. And then along with topic models, we will use some of the utility packages that we have in R, which are very popular. And if you have worked with R, I'm sure you have used them in some context or the other. And these are called the tidy utility packages. So we will use tidy verse and tidy text. So tidy text is something which helps us do some utility functions involving text data, right? So these are the ones that we will be using. So first things first, I have all of these packages installed, so I will load the libraries. That is done, and then I will proceed to read the data. Okay, so thus far for all the illustrations, we have been using the data on Amazon product reviews, but for this particular hands-on illustration, we will be using a slightly different data. So let me quickly open the data frame to give you a flavor of what the data looks like. So this data, again, this is also a review data, not the Amazon products review data. So this review data is actually something which is scrapped from Android Play Store. And in Android Play Store, there are reviews posted about all Android apps, and these reviews pertain to some of the mobile banking apps of some of the popular banks. So these are reviews of the mobile banking apps, the Android apps of some of the popular banks, and this is the serial number which was there in the data, and the first column is the key, is a unique identifier key which Quantdata creates for us. And obviously the text column is pretty evident. We purposefully we haven't kept the name of the bank out here, so there's not one single bank, but there are a collection of I think 4 5 banks or 6 banks whose reviews have been scrapped from Play Store. But we're not mentioning which banks they are because we don't have any intention to promote or criticize any bank out here. Anyways, so this is just for illustration purposes. So this is how the data looks like, and there are 7,401 documents out here, which is the size of the data, and that's pretty much the data that we will handle. And that's not too big data for us to at least look at the illustrations on the fly while I talk, and we'll see that. So let us create the corpus, and then we will also create the document term matrix using the quantdata function DFM. And along with creating the document term matrix, in tandem I'm doing some of the standard pre-processing operations. So I'm converting everything to lowercase, and then doing some stemming, removing the stop words, punctuations, so on and so forth. So all the standard pre-processing stuff I'm doing while creating the document term matrix. So I have created the document term matrix, but before proceeding further with the code analysis, there is something very important that we will have to do, right? So if you think of the document term matrix, it's basically in the rows you have the documents, and in the columns you have the terms. Now remember, before creating the DTM, there are some cleaning operations that we have done, right? So we have removed some stop words, removed punctuations. What if there were some reviews which only had stop words? It might sound weird, but somebody wrote something very trivial, or let's say there was some missing data. So essentially we can have scenario where some of the rows of the document term matrix can be all null, right? And which is something which we do not want to proceed with, because it will create problems for our analysis, particularly for the matrix factorization. So what we want to do is we want to inspect the document term matrix row by row, and wherever we see that the entire row is a null row, it's a 0, we will completely strip off that row from the document term matrix. So in order to do that, what I'm doing is I'm actually calculating the row total of the document term matrix. So I'm using the apply function on the DTM underscore topic model, and then I am applying the sum operator along the rows. So I have this second argument 1, which means that the operator sum will be applied along the rows, right? And then I am doing this cleansing operation, wherein I am saying that any row wherein the row total is 0, which means the entire row has just null entries, I will strip off that row from the DTM. So I'll do that, and quickly if I check how many rows I stripped off by doing this operation, you can see this, right? So originally there were 7,401 rows in the document term matrix, which was basically the number of documents I was working with, and now I have 7,397. So not too many, but there were some rows which got eliminated because they were all null rows. So I did this operation. So this is a trivial thing, but an important thing that you should do before you proceed, particularly when you are working with matrix factorization kind of stuff. So this is where the code thing starts. So we will run the LDA out here. So this function LDA in caps, so this is the function from the topic model package which implements the latent Dirichlet allocation algorithm, and I am using the dtm.clean matrix to do this, to run the LDA on, and this is the matrix after removing the null rows, and k equal to 4. So I am, how many topics am I hypothesizing? So in this case I am hypothesizing 4 topics, so that is the argument for k, and this is a initialization value required, and that is why we are providing this seed, because if you recall, the LDA algorithm is also an iterative algorithm, right? So iteratively it improves the topic term matrix and the topic document matrix until it comes to a stage when we are satisfied with its representation. So in order to do that iteration, we have to start off with some initial values, and that is the reason for which the seed is being provided. So let me run the LDA. So once the LDA statement is executed, what I will get is I will get an object which I have named as LDA, and then all the subsequent information that I need, and they are basically the two matrices resulting from the factorization of the document term matrix. Those I will get embedded in this object LDA itself, and I'll have to inspect and find them out. So so the algorithm is already executed. I will now inspect the object LDA. So let me look at the structure of the object LDA created here. So there are lots of things in this object. Looks quite clumsy, but then if I scroll down, I'll see something called beta out here, right? So, and before that you can look at the things like terms and documents. These things also you can look at. So terms actually tells you that how many terms were used to run the algorithm. So there were a total of 2963 terms in all the documents that we were considering here. So unique terms, 2963 unique terms, and then the algorithm is run on 7397 documents, which is the number of documents we were left with after deleting the null rows. And then comes something which is called beta and something which is called gamma. So this beta and gamma, these components of the LDA object, will actually give us the factorized components of the DTM, the two matrices that we are interested in. One of them will be the topic term matrix, the other one will be the topic document matrix. So no need to memorize which one is what, because if you look at the dimensions, you can easily make out. So if you look at beta, it has, the dimension is 4 by 2963, right? And you can immediately draw an intuition that 2963 were the number of terms which were there in the data, and 4 is the number of topics that you hypothesized, right? So obviously this is the topic term matrix. And then gamma, it has order 7397 by 4. So 7397 was basically the size of your data, number of documents you had, and again you hypothesized 4 topics. So this is the document topic matrix, right? So with that understanding, we will now try and extract these components from the LDA object. So let us first try and extract the topic term matrix. So we will do that using the tidy function. It's pretty straightforward. And once extracted, you see the topics, and I'm calling this extraction as topics. So if I look at it, so it looks not so easy to visualize. So everything is it's pretty much in long format rather than wide format. So topics, terms. So you see a particular term appears 4 times here because we are considering 4 topics, and then we have their corresponding probability distributions. So we want to visualize this in a slightly more intuitive way, in a slightly more understandable way. So that is why we will use the reshape function, which is used to reshape data frames and matrices, and we will use the reshape library, and then we'll use the dcast function to organize the data frame topics in a slightly more intuitive way, and I'm calling it distribution term over topic. So let me run it, and it's easier to understand by seeing it. Yeah, so this is what it is. So here, if you see, I have the terms as the first column, and then I have the probability values for this term across the four topics. So I'm hypothesizing four topics out here. So what does this give me? This matrix actually gives me the distribution of term over every topic. So the first column gives me the distribution of all the terms across topic 1. Then the second column gives me the distribution of all the terms given topic 2, so on and so forth, right? So this immediately gives me the uh, topic term matrix. And if you see, right at the beginning of the data frame here, there are some junk values, some numeric values and some other junk values. So I didn't do the pre-cleaning quite diligently, so I just did some standard stuff. But I think when you will actually work, so at this stage, what I will do is, once I have identified these things here, I'll again go back, remove these junk values, and rerun the topic modeling. But that's something which I'll actually not do now, because it's for the purpose of illustration. But when you are actually working on a project, you will obviously be taking care of these factors. So before proceeding further, let us completely satisfy ourselves that the columns of this matrix that we saw is actually giving us the distribution of every term given every topic. If that is the case, then every column should add up to 1, right? Because the probability distribution of all the terms in every topic should add up to 1. So let's see if the columns add up to 1. So I'll quickly do a sum here, and I'll sum what distribution term over topic, and yeah, let me take the first column maybe and see what is the sum. Yeah, so the sum is 1, right? So the first column represents the, let me open it once again. Yeah, the first column represents the distribution of terms over topic 1, so which obviously should add up to 1, because these are probabilities of different words in topic 1. Similarly, if I look at this for, let's say, topic 2, it should again be 1, and it should be 1 for all the four columns. So we can, to satisfy ourselves, we can do that check. So for 3 also it is 1, and then for 4 also the column should add up to 1. It does, right? So we satisfy ourselves that we have obtained the distribution of term given topic, right? Now the most important one of the most important part of topic model is, if you have segregated your text data into 4 groups, how do you really interpret these 4 groups? So what is the context of these 4 groups? So for that, we will be looking at what are the most probable terms across different topics. So I'm picking up the top 20 most important terms for every topic. So I'm using some operations out here to do that, and then I'll plot that. So not going into the nitty-gritties of the operation here. So this is some data wrangling steps that I am following out here. Anyway, I'll make the code available to all of you, so you can look at the intermediate steps in more detail. So if I plot this, this is looking very cramped. Let me zoom it out. Yes. So you see, this shows me what are the 20 most informative words in each of the 4 topics. And it is by looking at these words, I will be able to create a label for this topic. So I can say that topic 1 pertains to so and so context, topic 2 pertains to so and so context, etc. So if I look at topic 1, what are the words coming out here? Useless, update, transaction, time, terrible, poor. So obviously it's criticizing this is a topic 1 is a collection of reviews which is criticizing the mobile app and saying that it's useless. Transactions are very difficult to do. Then that what terrible is there. Then update. So I think it's talking about some update of the mobile app which happened, but still these problems are out there. So you can get some sense out of how to label this group by looking at these words. And then if you look at topic 3, so it again talks about worst work. So again transfer. So some negative words out here, but there is one term that you see, fingerprint. So possibly people are talking about fingerprint sensor, use of fingerprint sensor for logging into the app. So these kind of things are there. So essentially you can look at the topic term matrix and then plot the top 20, or how many you want to plot is completely up to you. So I am plotting the top 20 words every topic. You can plot the top 10 or top 30 and then try and find out what is the exact context about that topic. It can often happen that possibly you are not getting the context right, or it's a mixed context that you are getting, that no single topic is giving you one clear context. So that is where the iterative nature of topic modeling comes into play. So you have to then try with a different value of k, which is the number of topics, and then iteratively try and find out the representation which works best for you. So it's not all science, it's a little bit of arts as well, actually a lot of it. Okay, so we have looked at the topic term matrix and what kind of information we can derive out of that. Now we will look at the other matrix that we obtain by factorizing the document term matrix, and that is the topics by document matrix. And as we have seen in the LDA object, that matrix is stored by the name of gamma. So we will extract that matrix. And once again we will do some decast operation to represent the matrix in a more intuitive format. That is done. Distribution of topic over doc. So this is the one, right? So this matrix actually gives me the distribution of topics over documents. So given a document, what is the probability that topic 1 is present in that document, topic 2 is present in that document, topic 3 is present in that document, etc. So it gives me those conditional probabilities, conditional probability of a topic given a document. So obviously, this is a probability distribution over topics given every document. So the row sums should be 1, right? Each of the rows should add up to 1. So let us check if that holds good. So we'll actually create a column in the same matrix where we will have the row sum, and we'll see how does it look like. Yes, so we have created a row sum. I called it total probability. So that is adding up to 1, right? So for all the individual documents, the topic probabilities are adding up to 1. So that is, once again gives us the satisfaction that these are indeed probability distribution of topics over documents. Now, how do I interpret these numbers? So if I look at the first record maybe, so it tells me that the first document, 64% of it is from topic 1. So topic 1 is the predominant topic as far as document 1 is concerned. Then the second row, which is again which happens to be the 10th document in the order in which it appeared in my data, I see that again topic 1 is present with probability 0.59. So again topic 1 is the predominant topic here. However, if I look at topic 3 in the third record, sorry, then I see topic 3 has a probability of 0.58. So this is the maximum probability, and it gives me that topic 3 is most predominant in this record. And in the fourth observation, if you look at its topic 2, which is the highest probability value, and it's very highly polarized actually. So the fourth observation is very highly polarized towards topic 2. So ideally, you'd like to have more and more cases where the topic distributions in a given document is highly polarized towards one particular topic. So in this case, we have seen the highest probability value for the first observation was 0.63, for the second was 0.59, and then 0.58, and then 0.8. So these are decent values. So the highest values are quite highly polarized. And in fact, by looking at this distribution, you can do a one-to-one assignment of topic to document. So if you were to make a statement that I want to say that every document should be mapped to a unique topic, whichever is the predominant topic in that document. So you can simply pick up the topic which appears with the highest probability here, and then say that in this case you can say that the first document pertains to topic 1, second one pertains to topic 1, third one pertains to topic 3, and the fourth one pertains to topic 2, so on and so forth. But then that kind of an inference will only be appropriate if the highest probability is high enough. So if you have a scenario which, let's say for this case, in this data, if you have a scenario where for any document all the 4 topics have a probability of everything hovering around 0.25, it won't be, even though you will get a maximum, but it won't be the right statement to make in that case that which is the predominant topic in this document. Okay, so this is how the distribution of topic over documents look like. And once again, using this distribution, you can find out what are the predominant topics in every document. So this can also be used for subsequent supervised learning task as well. So when you use your document level data for doing any supervised learning, one of the features that you can use is what is the predominant topic in this document, or maybe what are the top 2 most prominent topics in this document. So these can be features which can be used for subsequent supervised learning as well. And that is why this matrix is also equally important, because it actually gives you the topic representation at a document level, and that is the level at which you will do the supervised learning task, if at all you have to do it. So one last thing that you can check is we looked at the distribution of topics every document, and we satisfied ourselves that the rows add up to 1 as they should be. If I kind of look at the average of the columns here, that should tell me that on an average in the entire data, what is the relative presence of topic 1, topic 2, topic 3, and topic 4. These are the 4 topics that we are hypothesizing here. So if I calculate these averages, you'll see that I get an average that topic 1 is present with in the entire data. Topic 1 has an overall presence of 0.17, similarly 0.27 for topic 2, and so on and so forth, right? So that kind of an interpretation also I can get. So if you see, this is also a good thing to test, because if you see that a certain topic has in the entire data has a very low probability, let's say 0.05 or even lower, then it is worth considering that do you really want to look at that many number of topics. So in this case, let's say out of 1, 2, 3, 4, had there been one of the topics where the average probability across documents was, let's say, 0.02, then the immediate thought for me would have been, do I really want to keep 4 topics here, or should I bring it down to 3 topics? Unless, of course, those 0.2% cases which pertain to a particular topic is a topic of specific interest. Otherwise, I'll typically not like to have a topic which is very rarely present in the data, unless of course it is of specific importance. So that was about topic modeling. How do we implement topic modeling and the latent Dirichlet allocation algorithm using R? It's fairly simple, way far simpler than how the algorithm actually looks like, the theory of the algorithm looks like. The implementation, fortunately, is much simpler. So that brings us to the end of this session. I hope it was useful for you, and I hope you will use it back in your work whenever you're doing topic modeling. Stay tuned for more sessions, and goodbye for today.